I kind of left you hanging at the end of the last video. I had this problem on the screen here, the Laplace transform of the integral from 0 to t of e to the negative tau cosine of tau d tau, and we didn't do it then, but we're going to do it now. First, I want to remind you of what the convolution of f and g looks like. We have f star g is the integral from 0 to t of f of tau, g of t minus tau d tau. Well, we have the integral from 0 to t here, but there's no t minus tau. And in a situation like this, what we can do is we can envision that g is equal to 1. So this integral, with arguments that are just tau and no t minus tau, is interpreted as a convolution of e to the negative t times the cosine of t. And that's exactly how we're going to approach this. It's the Laplace transform of e to the negative t times the cosine of t convoluted with 1. That means the transform of the convolution is the product of the transforms. So we have the Laplace transform of e to the negative t times the cosine of t times the Laplace transform of 1. E to the negative t times the cosine of t is the cosine transformed, but with a shift. And so we have s plus 1 divided by s plus 1, the quantity squared, plus 1 for the cosine with the shift. But then for the Laplace transform of 1, we're going to multiply that by 1 over s. That just adds a factor of s in the denominator. This idea is going to carry through into the idea of a transform of an integral. When g of t is 1, the Laplace transform of g is 1 over s. So the Laplace transform of the integral of f of tau d tau, tau going from 0 to t, is f of s over s, where, just as we saw in the previous one, the s in the denominator is coming from envisioning that we had a convolution, one of the functions involved of which is 1. So that one gave us this s in the denominator down here. Envisioning a 1 here is giving us an s in the denominator here. And then we are transforming f of tau. As usual, that transform rule gives us an inverse transform. The integral from 0 to t of f of tau d tau is the inverse transform of f of s over s. And so if you have a function of s and a factor of s in the denominator, we can inverse transform the function into an integral. In this example, we're looking at the inverse transform of 1 over s times the quantity of s minus a squared. We could use partial fraction decomposition, but I'm not going to because you've seen that a bunch of times, and I want to show you what it looks like to use this new rule that we just saw. First, I'm going to rewrite the function. It's the inverse transform of 1 over s times 1 over s minus a, the quantity squared. I'm going to connect the factor of 1 over s with the s in the denominator of f of s over s. That makes 1 over s minus a, the quantity squared, the transform of some function f. 1 over s minus a, the quantity squared, is the Laplace transform of t to the at, right? It's just an inverse transform of a t with a shift. So that te to the at can go into an integral. So this inverse transform is the integral from 0 to t of tau e to the a tau with respect to tau. There's nothing exotic here. Using integration by parts, we get 1 over a times tau e to the a tau minus 1 over a squared e to the a tau, all evaluated from 0 to t. So we get 1 over a times t e to the at minus 1 over a squared e to the at plus 1 over a squared. As usual, when I skip all those steps, I encourage you to verify on your own. Our next example is not even a differential equation. It's called an integral equation. f of t is equal to 2 times the integral from 0 to t of f of tau times the cosine of t minus tau d tau equals 4e to the negative t plus the sine of t. Well, we're told to use the Laplace transform to solve the thing, so let's do it. Wait, what does solving mean? We have an unknown function f of t, and it's showing up in two places there. We need to figure out what the unknown function is. Let's hit both sides with the Laplace transform. The Laplace transform of lowercase f of t is uppercase f of s. This integral that I just read is the convolution of f with the cosine of t. And so we have the product of their transforms, f of s times s over s squared plus 1. On the right-hand side, 4e to the negative t is going to transform to 4 over s plus 1, and the sine of t is going to transform to 1 over s squared plus 1. We want to isolate f of s, and so what I'm going to do is I'm going to gather together, well, I'm going to factor it out of the terms that we have on the left-hand side, and inside the parentheses that I'm multiplying by f of s, we get 1 plus 2s over s plus 1. I meant s squared plus 1. On the right-hand side, we're going to get common denominators. That's going to look like 4s squared plus s plus 5 divided by s plus 1 times the quantity of s squared plus 1. Getting common denominators for the factor multiplied by f of s on the left-hand side means multiplying 1 by s squared plus 1 over s squared plus 1. You'll note that means we're going to end up with s plus 1 the quantity squared over s squared plus 1 times f of s is equal to that 4s squared plus s plus 5 divided by s plus 1 times s squared plus 1 on the right-hand side. The s squared plus 1's divide out, and isolating f of s is going to give us 4s squared plus s plus 5 divided by s plus 1 the quantity cubed. And for this, we do need partial fraction decomposition. I'll just say that that's going to be a over s plus 1 plus b over s plus 1 the quantity squared plus c over s plus 1 the quantity cubed. I will let you verify that when all is said and done and we apply the inverse transform, that f of t is equal to e to the negative t times the quantity of 4 minus 7t plus 4t squared. If you thought the equation in the last example was weird, hang on. We've got something called an integro-differential equation. And if you've got another way to pronounce that, power to you. An integro-differential equation has a derivative, dy dt in this case, and an integral. We're looking at dy dt is equal to 6 times y of t plus 9 times the integral from 0 to t of y of tau d tau equals 1, and an initial condition of y of 0 is equal to 0. The integral that we see in this equation is actually the convolution of 1 with y of t. That said, we're going to apply the Laplace transform to the equation and then solve it. The transform of dy dt is s times y of s. The transform of 6 times y of t is 6 times y of s. And then we've got 9 times the transform of 1 times the transform of y. The transform of 1 is 1 over s. So I'm going to write this as 9 over s times y of s equals the transform of 1. You know, so many people will write down a 1 over here on the right, but the transform of 1 is 1 over s. So try to avoid that mistake. I'm going to clear the fraction here by multiplying everything by s. We get s squared times y of s plus 6s times y of s plus 9 times y of s is equal to 1. Factoring out, we get s squared plus 6s plus 9 all times y of s is equal to 1, which then gives us that y of s is equal to 1 over s plus 3, the quantity squared. That inverse transform is t with a shift. we get that y of t is equal to t e to the 3t.